Hello, and welcome back to Oceanography 106 Lab. Last week, we went over sediment classification and sorting and wrapped up the geology unit of this course. Today, we are moving into chemical oceanography with a lesson on ocean salinity. Salinity is defined as the sum of all dissolved ions in water, that means positively and negatively charged elements, expressed in the units grams per kilogram or parts per thousand of seawater. Salinity has been expressed in a variety of ways and with a variety of units, including grams per kilogram, parts per thousand, or parts per million for very small concentrations. Parts per thousand is a unit we will use in this lab, and it may seem a bit odd. Look at the percentage sign. Is there something not quite right? When we express a percentage, it is literally parts per hundred, with 100% being the maximum. If we want to demonstrate parts per thousand, we can show it as the amended percent sign with the extra zero on the bottom, or as PPT. Since the 1960s, the use of a conductivity meter as pictured has become more popular as the cost of these units has declined. Conductivity meters do not directly measure salinity. Rather, they measure the capability of water to pass an electrical current through it. This is related to salinity because saltier water can conduct a greater amount of electricity. Conductivity meters are useful because they are very easy to use, as you will see in this lab. They are cost-effective and they provide an instantaneous reading. However, they did create the need for an international standardization of salinity units. Therefore, the development of the Practical Salinity Unit, or PSU, was introduced as an international standard. However, grams per kilogram, or parts per thousand, are often still used to express salinity. So how much salt is there? On average, the oceans are approximately 35 parts per thousand, or grams per kilogram salt, which translates to 35 grams of salt per kilogram of water. Remember that salts are not limited to sodium chloride, the table salt that you may be used to. Most of the natural elements on the periodic table are represented in various quantities in ocean water. There's a wide range of salinity depending on the environment surrounding a body of water. In a freshwater system, one is likely to find salinity lower than 2 parts per thousand, or grams per kilogram. An estuary system, or a brackish water system, is one in which fresh water mixes with salt water and frequently have a wide range of salinities, anywhere from 0.5 to 35 parts per thousand, with an average around 14 to 17. An example of an estuary is the Chesapeake Bay. Around the mouth of the Chesapeake Bay, where Old Dominion is located, we find salinity much closer to 30, and that value will decrease towards the north as the river input is typically very low in salinity. Therefore, we see a significant gradient moving down the bay. The oceans, on average, have a salinity of around 35. It does vary somewhat based on the geographic location of the oceans. There are some bodies of water, however, that are significantly higher in salinity than the oceans. A great example of this is the Dead Sea, which has an average salinity of approximately 340 parts per thousand. The water in the Dead Sea is actually so salty and dense that when you enter it, you float. The natural water cycle drives the variation in salinity on a global scale. In places where evaporation exceeds precipitation, salinity increases. In places where precipitation or ice melt is greater, salinity tends to decrease. The major variation is the number of water molecules available. The dissolved ions that comprise salinity stay in constant proportion to each other, but the process of evaporation and precipitation change the amount of water. The difference between evaporation and precipitation in a given area helps us to determine salinity in that area. This chart shows how salinity changes by latitude. As you can see by the scale, the changes are still rather small. At the equator, evaporation is lower than precipitation. Why might that be? Think about where many of the world's rainforests are. In areas where evaporation is greater than precipitation, the salinity increases by as much as 1 part per thousand. This lab will be broken into 4 parts. We will be testing the accuracy of each of these 4 methods of measuring salinity. They are conductivity meter, the most accurate, then hydrometer, light refractometer, evaporation, and weighing. The conductivity meter comes in many forms, but we will be using the handheld type as located on the bottom left. The more current a conductivity meter detects, the higher the salt content. A refractometer measures the bending of light waves. A higher salt content is associated with a greater bend. This is what it looks like when you place a sample of ocean water in the refractometer and hold it up to a light source. A hydrometer measures the density of a fluid relative to the water sample it contains. Density increases with increasing salinity. We can use a chart to convert these density values into salinity values. The hydrometer measures the weight of the water displaced by its volume. The lower the density of the fluid, the further the hydrometer will sink. The saltier the water, the higher the hydrometer will float. This is an example of the seawater density chart. You will see this again in the lab videos. Finally, we will be evaporating salt water to determine the residual amounts of salt that remain after all the water is removed. There are several reasons this method is only rarely used now. It takes a long time, it's less accurate, and it is difficult to determine when all of the water is evaporated, but it is still the least expensive of the methods. This week's lab has been posted as a series of videos on Blackboard. Make sure you also find the density conversion chart. Good luck!